Hello and welcome to this webinar on nonlinear and buckling analysis using GSA. Do the nonlinear first and then look at the buckling following. So, nonlinear basics. First of all, when you're doing linear analysis, there are various assumptions in that analysis. And if the assumptions are met, then the analysis is genuine, effective, whatever. So, for example, the displacement-strain relationship is linear, which is, okay if you've got small displacements. Likewise, the stress-strain relationship is linear. And it says the equilibrium is established at the original non-deformed geometry. This means that it's assumed the geometry doesn't change during analysis. I mean, you do get deflections, but it's assumed they're not significant deflections, and therefore for the equilibrium equations in analysis, it's assumed that nothing actually moves. End results: linear equilibrium, linear load displacement, linear load forces. This means that if you want to go from an individual load case to an ultimate limit state case, you can just multiply the results by the ULS factor and be happy that the results will be okay. But the thing to remember is if your deflections and your strains are large in the model, the linear analysis won't necessarily be appropriate or accurate. On the other hand, if you're dealing with non-linear analysis, you need to look at non-linear analysis if you're getting large displacements, say flexible structures or structures exhibiting large load. I mean, imagine a cable net structure, for example. They deflect quite a lot to take up the load. Elastic plastic materials such as steel, yielding plastic hinges and so on, or alternatively materials like rubber, where you exhibit very large strain even though the materials still remain in the elastic zone. So, end result, all the equilibrium and displacement and forces and so on have a non-linear relationship to the original loads. And because the equilibrium is based on the deformed configuration, and this means that the path loads loads can go down the structure in a different way depending on what the loads are on the structure, and so it's quite inappropriate to combine the analysis results. Okay, so geometric nonlinearity to begin with. And here is a linear analysis problem: cantilever, axial load, shear force, and because you're not dealing with any deformation, the reaction F is equal and opposite to the applied load P. The shear load V is equal and opposite to the applied load Q, and the moment is Q times the height. Good first year university stuff. When you're getting large deflections involved in this sort of structure, then things become a little more complicated. So the reactions F, V and M are actually become a factor of the two applied loads. And you'll notice as well that we have this applied load P and this deflection delta, and hence we have what's known as the P delta effects. So let's look at an example of this. I've got some examples prepared previously. First of all, I have a cantilever column, very similar to the diagram I just showed. This is about 10 meters tall with some loads applied. And I've set up previously 3 analysis tasks, each with the same loads, but static, a p delta, and a non-linear analysis on these. And because the loads are quite high, we will see quite a reasonable difference between the results. So that's all worked good. Okay. So the results. I mean, if we take the static linear analysis, and I just switch on my bending moments, shear forces, and axial loads, and annotate everything. Oh, and let me just tweak the numbers so I'm not getting the very small numbers showing up. Okay, so applied load of axial load of 2000, getting axial load of 2000 all the way down, horizontal load of 2000, which means we get a 2000 kilonewton shear and a 10,000 kilonewton bending moments on this column section. But it is deflecting over a reasonable amount. So if we look at the P delta option, we'll note that the axial load remains constant down the column, but we are getting shear force and bending moments in the upper part of the column, and we're also getting more deflection on this structure. And similarly, if we go for the non-linear, we're getting moment and shear force to the upper reach, but we're actually getting less axial load, curiously enough. But we're also getting an overall rotation of the structure. Now if I go to my saved output views, we can see from the displacement, A1 is the linear, A2 is the P delta, A3 is the non-linear. We can see that all three loadings are deflecting quite a lot horizontally by different amounts, but under vertical deflection, only the non-linear is actually giving us a sensible looking vertical deflection. In some respects, because the P delta analysis is not giving us a proper rotation, it's just giving us axial shortening, not the rotational effects. The P delta is structurally deflecting too much for the P delta analysis to actually give us sensible results. So whereas the non-linear results are much more sensible looking. Likewise, we are getting interchange between the axial loads and the shear force, which we are not getting on the other load cases. So large deflection structure like this, the non-linear, is giving us much more sensible looking results. Another example where we'd use non-linear is this example. If I look for an isometric, we have a point load in the middle of the beam, but this beam actually has, apart from the pins at the ends, also has a pin in the middle. This is a 3-pin beam, and you'll remember from our first year structures lectures, this won't work under a linear analysis. What will happen in reality, of course, is at that point will deflect down until these members stretch and take up loads under axial load. And if we run a non-linear analysis on this, we find exactly that we now have quite a significant axial load on those beams, because the structures had to deform to actually carry that load. Now alternatively, if we actually take this 3-pin beam and actually delete half of it, so I've now got a pinned cantilever. Let me just remove the release on that just to make sure everything's stable. This is now a pinned cantilever. If I rerun the analysis on this, and look at the deflected shape, you see this this pin cantilever has deflected, so it is hanging straight down, which is just what you'd expect from a real structure, and sort of analysis you can do with GSA, because you can't do this sort of analysis with a matrix method at all, but you can with GSA. Another example of these geometric non-linearity is what we call the snap-through calculation. Now, the snap-through, and this is an arch, but likewise could be a portal frame. We have an asymmetric load on this structure, and we can actually increment the loading until the structure fails, so it actually snaps through, and rather than being an arch, becomes a catenary. So in the nonlinear analysis, this time we have an automatic load increments set. So we'll start off with a low load and we'll gradually increase the load, changing the geometry each time until we get to final failure. And the final failure is controlled by this displacement control, node 8 is the node in the middle. I'm saying once it translates, it moves more than the meter, then stop the analysis. Likewise, we could have a maximum load factor as well, which will give similar results if we know what that factor might be. So let me just edit that, just take that old load factor off from the last time I ran the analysis, and run the analysis again, and we'll see it in action. So you can see in the report view, it's gradually increasing the load, and you'll see occasionally in the deflected diagram when it shows up how the structure is deflecting. And you see we've reached the limits, and we can see this arch has now inverted, and we can see on the results the deflection changed. And you'll note in report view it says we can evaluate the load capacity by plotting the load factor displacement curve. Now you can find this under the chart views, which is under nonlinear analysis. We'll look at this, and we can see on this chart that as the load increases, the middle point, it deflects up a bit to begin with, and then reach the point where it snaps through, and we can actually right click and get the coordinates out of here, and we can see, if you can read that, it snaps through as a load factor of 4.26. Eventually factor of safety 4.26 against snap through for that particular loading, but yeah, obviously there might be other load cases to check, so this can be a very useful operation for these types of structures. Okay. GSA, we also have nonlinear elements, and some you might be familiar with: struts and ties, compression only and tension only elements. We also have cables, which are a tension only chain of elements where the tension remains constant along the chain, and also fabric elements, which are tension only two-dimensional pieces of fabric, quite literally. Examples of these. Let me open up my here is an example of some non-linear structures. So I've got 3 bays, and I've got first bay cross brace with bars, second bay with ties, third bay with struts, and with horizontal loading on this, and also these main beams are pinned as well, so they won't be carrying moment across. Now these are non-linear elements, but we can run a linear analysis on them, and what will happen if you run this analysis, you'll note you get a warning that tie elements and strut elements can cause the GSS solution, that is the linear solver, to become iterative. What this means is that when you apply this load, this tie here will go into compression. GSA will say it's a tie, can't be compression. It will switch it off and then rerun the analysis. Now sometimes you might find it can oscillate between two conditions, in which case it's worthwhile adding in a normal or horizontal load. But so if we actually look at the results, we'll see that this tie taking up load, this strut's taking up load, but this strut, that tie, and these other members haven't picked up any load at all. Whereas in the bar end, the two bars are picking up very similar loads to each other. We also have a model here to show cables. If I just change these two cables back to ties, and you can see we have a point load here, a tie to a support point, and another tie, another support point. And if we run the nonlinear analysis on this, you see the end result is an axial load there. And if I add in my resolved displacement, resolve reaction, and annotate all those, we see load 20, axial load 20, reaction 20. Straightforward to expect. But if we're doing if these were cables, on the other hand, result would come a little bit different. If I rerun that, and you see with the cables, because the tension is remaining constant, these essentially pass over this node up here, so you get a higher reaction. This node becomes effectively like a pulley. We then get reaction down here. So cables can be very powerful, very useful if you know what you're doing with them, but they have to be used with caution, because the results can be unexpected if you're not careful. Okay. Material nonlinearity. Now, with a real engineering material such as a piece of steel, you'll get a stress-strain curve which looks something like this sketch here. So, elastic range, yield, plastic yield, strain hardening, and eventual failure. With GSA, we take a slightly simplified version of this, which we have linear elastic part and the yield stress, and then a constant plastic stress. Now, this enables us to form plastic hinges and elastic plastic hinges as well, which we'll see. So, if I've got our model here, this is the wrong model. This is the model I want. This is a two-span beam with a UDL on there, and I have set up a user-defined material which is elastic plastic isotropic material, which has an ultimate stress capacity. Note there are it's a U stress. Notice it has got ultimate stress and hardening properties in there. GSA itself doesn't use these, but if you're using GSA as a preprocessor for something like LS Dyna, then these factors are then taken into account. I've set up a linear and a non-linear analysis, and in theory the contents are the same, but if we run these, we'll see we get some warnings. Under linear analysis, we see we get a warning which says the non-linear material behavior will not be taken into account because it's a linear analysis. But on the non-linear analysis, there's a warning about plastic yielding, and then saying that actually we are getting elements yielding in bending. So results on this. If I just do a volume on half the structure, you can see a bit better. We can see for the linear analysis we're getting a peak moment of 155 and a sagging moment of about 88. With the nonlinear, the elements have yielded at the top, and so we've got a full plastic hinge at the top, 107 kilonewton meters, and in the middle where it's sagging, we're reaching 105, which means the structure has very nearly completely failed, but it's reaching the end of its elastic plastic range. I mean, for example, if I just draw on the screen here, stress strain or strain planes. Imagine there's our normal elastic strain plane. We get a straight line like this. Once we reach the elastic limit, we then actually get a elastic plastic stress distribution, and at the end we then get a full rectangular plastic distribution. This structure would actually be unstable in that situation, so it would fail if we had full plastic hinges forming in the midpoints of these as well as the end. Now let's look at general nonlinear. Let's look at buckling. Now buckling does involve nonlinear, but also we have linear and nonlinear buckling in GSA. Now linear buckling is sometimes known as eigenvalue or modal buckling. Nonlinear, when we are in elastic nonlinear, elastic plastic nonlinear, elastic plastic takes into account material yielding aspects. So linear analysis, linear buckling, as you know, when you increase the axial load on an element, it changes its stiffness. And if you increase the compression, the stiffness of a member reduces. And so what the linear buckling analysis is trying to do is find out what the load factor is at the point where the stiffness becomes zero. And there are a number of ways the structure can buckle, and so it will find a number of load factors. Note that this horizontal load will have very little, have some but not much effect on the buckling capacity, but because it's linear and the equilibrium is found in the original undeformed shape, this deflected value is not really crucial. The deflected shape is crucial, but not how much it's moving. In fact, GSA will normalize, that is, adjust the deflected shape until the maximum deflection is 1 meter. Note also that in reality this could be 1 meter in either direction. So you can get the axial loads, but you can't get the deflections values, and you can't get the moments, because obviously the moments are based on that large deflection, which is not real. On the other hand, the non-linear buckling analysis is what we call MOSEP. It's gradually increasing the loads and finding the deformed geometry at each step. So the deflection is actually the real deflection of the structure. And if you're getting the plastic materials in there as well, you're getting that will be included. To look at it another way, here's a graph of load against displacement. And if you've got linear buckling, it finds the load, but the displacement could be anything. With the non-linear, as the load increases, the displacement increases as well until it reaches close to the linear buckling calculated value. And if you've got plastic values, plastic material values taken into account, then the buckling load will actually be quite a bit less than the elastic and linear and non-linear buckling calculations. So, see this in action. Here we have a simple structure with a unit load at the top. Now, we have a column section with a lateral restraint and some beams at the top to give it some sort of positional and rotational restraints, and at the bottom I just have a positional restraint from this pin. And you note also that these beams are broken up into at least two pieces. If you don't do this, you won't get proper buckling results. Let's first of all look at the modal buckling I've set up. So modal buckling is a linear eigenvalue buckling, and I'm asking for 4 modes. We can ask for a load cutoff value. So if we let's say we were using working loads, we say give me buckling up to a load factor of twice applied load or 3 times applied load or something like that. On the other hand, in this model I've used a unit load, which means that it will actually be working out rather than factor of safety against buckling, the work out the actual buckling back. So you give me the multiplier on the applied load, the watch point it buckles. If I analyse this, we'll see that we have our first buckling mode, major axis, with a load factor of 642, and minor axis bending 819, another minor axis 1500, and a major axis double curvature 1900. So 4 different ways that this structure can buckle, but the most likely is going to be the 642. Now note, of course, this is a simple structure. With a more complex structure you might get a number of buckling modes with quite a similar load factor. If I run the member or non-linear buckling, this is slightly different. I'm saying I'm interested in these 6, 7, 8, 9, which happen to be these 4 column sections. And if I run this, it's incrementing the loads until such a point where it feels the structure has failed or it's reached some other limitation. And again, see, it's buckled quite similar shape to the first modal buckling, but you say, if it says plot axial force deflection curve to find the capacity. So let's again look under the chart views, nonlinear analysis, nonlinear buckling, and we can see there that as the load increases, deflection gradually increases, and then it reaches the point where the structure basically gives, and we can use this to back calculate a safe working load on this structure. And if I call up my coordinate points, we can see, well, the modal buckling gave a capacity of 642, non-linears reached a limit at 633, so it's getting quite close to the modal linear buckling capacity, but it's saying much more than this, and the deflections will be large, very large. I mentioned earlier about non-linear analysis cases and combinations. This can sometimes cause confusion amongst when you first start on GSA. Load cases, this is where you apply the loads, obviously, and these usually have reference L1, L2, and so on. They have analysis cases with an L reference, and You can apply load factors at this point, and you have combination cases where you can combine multiple linear analysis cases, and you can apply factors, and you can produce an envelope to kind of worst case. Put another way, by default, each load case produces a linear analysis case on a one-to-one relationship. You can override this, but these will have the same number and the same name, so they will appear very similar. But being linear, you can multiply and combine these together and then produce an envelope result. With nonlinear, you have to multiply and combine the various load cases as part of the nonlinear analysis up front. And so in the combinations, it's only appropriate to do an envelope. It's not right to do combination cases where you multiply and add nonlinear results together, because the results will not be accurate at all. With GSA, the nonlinear solver uses a method called dynamic relaxation, and dynamic relaxation is essentially a dynamic method of finding results. So you apply a load, forces produce accelerations, accelerations produce stresses and strains, and so on. And if you imagine this structure here, if the structure is moving around, there will be the unbalanced positions where the various parts of the structure they're stationary, but you've got maximum force on these nodes, maximum acceleration, and so no speed, no kinetic energy, but maximum acceleration. And these are the sort of the unbalanced positions. Whereas what we're looking for is the equilibrium position, where you've got zero acceleration, zero residual force on the elements, but they will be traveling at maximum speed and have maximum kinetic energy. Same sort of principle. Now this feeds into our damping system, because it's a dynamic method. You need to put damping into the system to make sure that it doesn't oscillate around the answer. And we have two methods: viscous damping, which is a bit like sort of oil, where the damping is proportional to the speed that the various elements are moving at within the analysis. Or there's kinetic damping, which works out the position of maximum speed, maximum kinetic energy, and says that's probably the equilibrium position, so it readjusts the coordinates of the nodes to those points, and then reapplies the loads and sees what happens. And either will converge. Sometimes one is better, sometimes the other is better. To put it another way, if you're looking at viscous damping, with no damping at all, the structure will just oscillate backwards and forwards around the equilibrium position without actually finding the definite answer or finding where the equilibrium is. If you've got the damping value which is just smaller than the critical being the optimum damping, the structure will overshoot and then come back and then converge the answer. And likewise, if the damping is too large, it won't overshoot, it will just take longer to reach convergence. And so knowing what the damping should be is quite tricky. So GSA has automatic damping calculations in there, which it will adjust as you go along. Sometimes these routines don't work, so you can go in and take manual control and actually adjust the damping yourself, part of the analysis.